Hello. In the previous few lectures, we had covered the cache memory, how it was used, and different details pertaining to it. And before that, we were covering main memory, right? Now we move on to a concept of virtual memory. So, when we are talking about virtual memory, yes, the hard disk is involved, but the main action is not happening here. So it is happening in the main memory and something in between. Okay, something in between the main memory and the processor, let's say. So that is virtual memory. Let's move on to that. Okay, virtual memory. When we are talking about virtual memory, yes, hard disk comes into play, and hard disk is used as a tool to implement virtual memory. And but remember one thing: hard disk is not virtual memory. So, so what is virtual memory then, right? So it is something that the name itself suggests. That is, it is a memory that is not physically happening or physically available. It is a memory that is only virtual, that it doesn't exist actually, that memory, but it is something that we give the process or processor. We let the processor or the process or the program running, we let it think that okay, this much memory is available. But what we do is we use a combination of main memory and some portion of the hard disk to accommodate this much virtual memory, or this feeling of virtual memory that the processor or that particular process has, right? So suppose that the processor or the process being run, it thinks that or it assumes, let's say it assumes that there is a 2 GB memory, but in actuality, in reality, there may be 512 MB or maybe 1 GB or something like that of main memory only. So what we do is we let the process think that okay, let it think that there is 2 GB memory, but we somehow manage something, manage this request, memory read and write request from the process using our 512 or 1 GB, 512 MB or 1 GB main memory and the hard disk. So this idea that this thought or this assumption that the program or the process takes that okay, there is 2 GB of memory available at its disposal, that is actually virtual memory, right? Virtual memory is not something that is there in the hard disk or anything. It is that understanding or that assumption that the process or processor takes that okay, this much memory is there. If the processor if the particular process thinks that okay, 2 GB of memory is available, but in actuality only 1 GB or 512 MB is available, then that 2 GB being assumed by the process, that is called virtual memory. And in this lecture and the subsequent lectures, we will see how this virtual memory is actually implemented, and how the rest of the actual hardware, how the physical hardware implements or manages the requests for read and write coming from the process or processor. So before moving into that, so why is there this requirement for virtual memory? Because suppose if we consider the 32-bit MIPS processor, it has 32 bits of address lines, right? So that it can effectively address 4 GB memory space. So and the process or any processor won't ask for anything more than 4 GB, and we can actually provide 4 GB memory hardware. Then why do we need virtual memory? We can provide whatever the process can use, right? Then why do we go for virtual memory? The thing is that when we are talking about the processor being able to address 4 GB, first of all, we may not actually completely use the capacity hardware capacity of a processor to address memory, right? So suppose if the capacity of a processor is to address 8 GB or 4 GB of memory, we may not provide it to begin with. We may only provide 2 GB or 1 GB depending on the particular condition. That is one thing. So actual hardware may not be available. The other thing is that the operating system itself takes some memory. Operating system, it has to keep on running, right? For any process we have to run, the operating system has to run. So the kernel of the process of the operating system, it takes some space. Then some space will be reserved for some other purpose. So even though if you are going full out and giving a 4 GB hardware as primary memory, main memory, that 4 GB fully may not be available for a process which is being executed, right? Or a program that is being executed. So what we do is, but the thing is that as a programmer, they may not know, okay, which of these spaces, which of the memory is available, how many RAM the actual hardware has. So what the idea is that let the programmer assume that, okay, the full memory is available, and he or she will design the program like that. It will assume that there is 4 GB or 2 GB or whatever. But what we do is we do some technique so that this much virtual memory that the program or process is assuming, we will somehow manage to entertain the write and read requests of these virtual memories to our actual physical memory. That is what we are going to do. Okay, now consider this image. This is the virtual memory. Suppose this is the virtual memory, this is the physical memory, and this is the hard disk. So in virtual memory, what is happening? Virtual memory means this is the view of the process or program. That is, the program or the process assumes that, okay, this much space is there, memory space is there, but actually only this much is there. So what we do is, when the program requests for this space, this memory, we don't actually give this. We have done some process called as an address translation, or using our earlier terminology when we had dealt with caches, we used the term mapping, right? So here also what we are doing is mapping. We are mapping the virtual address to a physical address, right? So what is a virtual address? Virtual address is the address that a process requests in the virtual memory, right? The process will be assuming, okay, this will have a address. So this address of the virtual memory is called as a virtual address, and it is translated somehow using some mapping procedure. It is translated to a physical address which is pointing to a physical memory, right? But all these all the virtual addresses may not be there in the actual physical memory. Then what we do? Then we take the help of the hard disk. So some of these things, some of these locations, memory locations or addresses, virtual addresses, may be mapped to the physical addresses in the physical memory, and some of them will be mapped to the hard disk. So what is the criterion to decide which goes in the physical memory and which goes in the hard disk? It is something similar to what we did in cache memory. So the thing is that what we are doing here with virtual memory, this mapping of virtual address to physical address, and we have to and managing this between hard disk and physical memory, this is very much similar to what we did in cache memory, right? Cache memory was this this exchange between physical memory, main memory, and cache memory, right? Similarly here, for managing this virtual address, there is some sort of arrangement between hard disk and physical memory. When we say physical memory, we mean main memory. And one more thing, each of these rectangles, these blocks, right, these are not individual address locations or memory locations. These are called pages. Okay, these are pages. So what is a page? A page is something very similar to a block in cache, right? Remember, we had a main memory block and cache memory block, right? So what was that? That was a collection of certain words. Like these many words was considered to be a block. Like that, we assume or we decide that, okay, these many bytes or these many kilobytes will be one page. So we in terms of cache memory, when the relation between cache memory and main memory, we call it a block. In the relation between virtual memory and physical memory, we call it a page. That's all. So there is a lot of similarity between it is very analogous, cache memory and virtual memory. So what we call in a cache memory as a block, so there is something similar in virtual memory, which is page. Like block size, there is page size. Like block offset, there is page offset. There was a miss. Remember, miss and hit. Miss was when the address searched by the processor is not there in the cache. That was a miss. Like that, there is a page fault. Page fault is when the page searched in the main memory is not available in the main memory. That is a page fault. Then there was something called as a tag, right? Tag was the certain bits of the physical address or actual address which was used to identify the block or set. So like that, there is a virtual page number or page number in general. So with this, we'll move on to more details of the virtual address. Okay, we mentioned that there is some address translation happening, right? So in cache memory, this was done using tag bits and some comparators and things were there. But in this part, that is in paging or in virtual memory, how do we implement this? This is implemented using the concept of something called as a page table. Okay, so what is a page table? Page table is nothing. It is like something like an array, right? So it has consecutive memory locations where the address corresponding to each virtual page number, that is the physical page number corresponding to each virtual page number we are keeping in the page table, right? Because when there is a request for a certain virtual address and we need to find the corresponding physical address, then what we do, we go and search for the physical address in the page table. So corresponding to each virtual page, there will be a physical page number, and it will be denoted in the page table, right? Then what we use that thing called as a page offset to find the specific value of the address. So we will come to that. The other thing is that this page table is something that is big enough, right? Because if we have say 2 to the power of 10 pages in our virtual memory, so corresponding that many page table has to be maintained, right? That such a big page table has to be maintained, and that should be readily available for the processor for looking up. So what we do is we actually implement something very similar to a cache. What was the concept of cache? Cache was something that exploited locality, temporal and spatial locality. So we do the exact same thing in paging. So instead of referring to the page table in the main memory every time, we implement something called as a translation look-aside buffer, which is in every sense a cache memory for page table. That is, the page table pertaining to the recently or frequently used pages will be saved in a specific hardware called as a translation look-aside buffer. So we will go into the details later. Okay, so with that, I think you might have gotten overview regarding virtual memory, the concept of address translation, mapping its similarities with caches, then the concept of page table, and the idea of translation look-aside buffer. So with that, I'm stopping this lecture here. In the next lecture, we will take up address translation. Thank you.